Okay, first thing, Sarah just told me that apparently there was something wrong with the homework that was assigned to be due today. And so after class, I will fix that and I will extend it by another 2 days because you weren't able to do it apparently. I apologize. Obviously, my mind has been elsewhere last couple of days, but my wife is absolutely fine. She's home recovering from the surgery. So I am pleased about that. I obviously am sorry about making a mistake on the due time for the homework. I wasn't here for lab yesterday, but I was told that everything went well. I put a post on Moodle with the data from the freezing experiment. And then after I posted it, I noticed that I had the room temperature and the hot water lines mislabeled. Clearly the one that started at the higher temperature was the hot water. So I've changed it here, but what is posted on Moodle doesn't have it changed. So just be smart about that. Remember, the hot one is the one at the higher temperature. So what are the things that you are getting out of analyzing this data? Well, what were the reasons for doing this data?
See which one freezes faster.
Okay, number one was to see which freezes faster, hot water or cold water, if you start with equal volumes and you put them in the same freezer. So how would you judge that? How many people have actually read the message you got from Moodle that I sent? Haven't. Okay. So how you would judge that is you would say, okay, freezing, maybe I should do it down here, yeah. Freezing, what we told you in class was that it freezes at a constant temperature if it's a pure substance. This wasn't pure deionized water. And so it's not perfectly that way. So just choose and say, okay, what is a reasonable, okay, come on. What is a reasonable temperature to say, okay, now it's finished freezing? And so I would say, oh, let's say 5 degrees below zero. And so which one gets to 5 degrees below zero first? The blue one or the red one? That should be an easy, quick answer. The blue one does, because it got here somewhat less than 1,600 seconds, whereas the red one was somewhat less than 1,800 seconds. And so what conclusion can you draw from that? Go ahead, Leah. The what? Cold water freezes faster than hot water. Is that what you had predicted? Okay, some yes, some no. Why would you predict that cold water would freeze faster than hot water? Okay.
Because the molecules are moving more slowly already, and so they don't have as much to slow down.
There's less temperature change necessary to reach freezing temperature, which means less heat that has to be removed to reach freezing temperature. And that's the same amount of heat necessary to freeze it. So there's a less heat total necessary to freeze the cool water compared to the hot water. So it makes perfect sense. Now, David, I'm going to pick on you because you were brave enough to admit you had said the other way. Why did you say the other way?
Well, I was just thinking, how you take a boiling pot of water out on a vertical day, throw it up in the air, and it instantly freezes. That was my observation. So.
Okay. Why?
Yeah.
Couldn't tell you. It was an observation. It's cool. I made a judgment based on it.
And you can read scientific articles about hot water freezing faster than cold water. My own personal hypothesis is, there are ways that you can make hot water freeze faster than cold water. And I think it has to do with evaporation. Because if you start with equal amounts of hot and cold water, the hot water is going to have more water that evaporates, which means by the time you get to freezing temperature, you have less water than you started with, which means you can freeze less water in less time because you have to remove less heat to freeze a smaller amount of water. So I believe that's why you can get the counterintuitive hot water freezing faster, is because at the end you had less water, so you froze less water. So our experiment turns out to match what you would have expected. Now, if we look at the other lines on here, the blue one, it doesn't instantly go down to minus 80. Why would it not instantly go down to minus 80? Because it takes time for the probe itself to cool. Remember, our thermometers are measuring the temperature of the thermometer, not of the environment. And so it took time for the thermometer to cool, and that's why it didn't instantly go to 0. So basically that gives us, that's the fastest possible change we could have had. Other things we're supposed to get out of this is Newton's law of cooling. What is Newton's law of cooling? Strong memory on that?
Strong memory.
Newton's law of cooling says the rate, or Newton's law of heating, the rate of heating or cooling is proportional to the temperature difference between the hot and cold substances. So if I have a temperature difference of, okay, if you go from, notice I blocked out the first 150 seconds here because there was something weird going on. You can see, for instance, the air temperature probe was constant until about 50 to 100 seconds, and then it started dropping. Well, clearly that wasn't realistic data for being in the freezer. So that's why I blocked out that first part, in case you're wondering. In science, you do have to analyze your data and say, there is a problem. You know what the problem is, and then you analyze what you don't have a problem with. But you don't just discount it completely and say it didn't happen either. Right? Just like with your data, you put a line through data that you believe is an error. You don't erase it. Okay, so where was I going with this? Okay, Newton's law of cooling or heating. If we start at 40 degrees, it'd be simple. 40 to minus 80 is 120 degrees difference between the temperature of the water and the environment temperature. And so Newton's law of cooling or heating would say that our rate of heating should be proportional to that 120 degree difference. Whereas if you get down to 20 degrees Celsius, then it's only 100 degrees between minus 80 and 20. And so it should be a slower rate of heating or cooling. So as the temperature of my water drops, the rate at which it's cooling should also be dropping. That's what
Isn't it negative 70 degree freezer?
well, it's negative 80.
It only goes to negative 71.
No.
Fast.
If it was only showing negative 71, then it wasn't sealed.
It never goes down.
No, it does. It was when Andrew and I were preparing on Monday, it was at minus 77 at that point. And I pointed out to him, it's not at minus 80, which means that it's not sealed perfectly. And so we opened it up. Sure enough, it had some frost around the edge that keeps it from sealing perfectly. But it is minus 80. But that's also not important for
So like the actual temperature difference doesn't matter.
the what?
The temperature difference between the 70 and the
Well, it's going to make the rate of cooling a little bit slower because it wasn't quite as low as it's supposed to be. But we're not actually making any calculations based on that.
okay.
Okay, so the point is your rate of cooling should be faster when your temperature difference is bigger. And how can we determine rate of cooling by looking at this data?
The slope.
Okay, the slope, because the slope is going to be the change in temperature per time. Rate of cooling is going to be the heat per time. But since Q is equal to MC delta T, Q over delta T is equal to MC change in temperature over delta T. So we can use one as a proxy for the other. So according to Newton's law of cooling, it should be flatter here than it is here. It should be steeper up here, flatter down here. Or this red line taken as a whole should be steeper than the blue line taken as a whole before you get to freezing commencing. So those are the comparisons to do to verify if Newton's law of heating or Newton's law of cooling was observed in this experiment. Final things to note, obviously, freezing stayed roughly constant temperature, and then it slowly started declining. And it probably didn't completely freeze until you got down to here, because you see a change in the slope there. So it actually probably was freezing this initial portion was at 0, and then you started freezing things that were impurities and finished freezing at about -20 realistically. That's probably when it became fully frozen. If you look at the salt water didn't start freezing until around -7, and it finished freezing down here at about -35. So what's the difference in the salt water and the non-salt water? Let's leave it at that. You know what? Aaliyah answers, just not loud enough for me to hear. I appreciate you answering. What did he say? Okay, salt water took longer to freeze, but it was greater impurities. Because of those greater impurities, you had a different fundamental behavior there. And then ultimately, they all come down to the same final temperature. And you can see here, the final temperature that it reached was around -75. It's not going to seal well when you have wires coming out either. So if it doesn't seal well, you have more heat flowing in, which means that you would have to pump the heat out faster to keep the temperature down to minimum. So you have this data on Moodle. Make sure you download it. You all have Capstone already on your computers from our trampoline lab, so you can open it in Capstone and analyze the data. Any questions about the data from lab yesterday?
Yes.
Go ahead.
I'm confused about why the air temperature one freezes so much more rapidly.
No, the air temperature one is not water, so it's not freezing at all.
Oh. Okay, thank you.
Any other questions? That one was there for control.
I was thinking about the room temperature water that we were doing.
Yeah, and that one did not freeze so fast.
Yeah.
Okay, let's get into the lecture. Ideal gases. What were the defining properties of an ideal gas? What made it ideal? It's dilute, okay? Dilute. That means that you have the ideal property that's associated with dilute is that the molecules have no volume. And being dilute approximates no volume because the spacing between molecules is very large compared to the size of the molecule. What was the other ideal behavior?
Perfectly elastic.
Perfectly elastic collisions if they collide and otherwise non-interacting. And we approximate that with high temperature, so the amount of energy associated with the interactions is small compared to the total energy, so you say, well, fundamentally didn't change. So those are two approximations. Now, this works pretty good for many gases. We're going to talk a little bit about evaporation today, and we'll talk about the partial pressure of water. Well, if you're close to boiling temperature or condensation temperature, it's not an ideal gas. So we can't use the ideal gas law to analyze the partial pressure of water at 102 Celsius. Being good chemistry students, what do you use in a situation like that? The van der Waals equation of state. The ideal gas law, the ideal gas equation of state, is P equals nRT. But the van der Waals equation, or I'm sure it should be pronounced van der Waals, right? P is pronounced as an F and W is pronounced as a B. That equation of state takes into account the reality. So it has one parameter that's the sticky parameter that tells you about how much energy you're going to lose in collisions, and one parameter that's the volume parameter that corrects for molecules not having zero volume. And so in a situation like that, if you use the van der Waals equation of state, you'll get a more accurate calculation. Now we're going to right now jump into the kinetic theory of gases. The kinetic theory of gases has as an outcome something we've already spoken about. What did I teach you temperature is really measuring? Humor me. What did I teach you? Not heat.
Change in temperature.
Yeah, it's measuring something about the motion of molecules. The average kinetic energy is what I taught you. The kinetic theory of gases is dealing with that. So suppose you have a vessel. Here we have a nice box, because boxes are easy to work with, filled with gas molecules. These gas molecules are bouncing around. They hit a surface and they rebound off the surface. If it bounces off the surface, there's going to be a force involved, right? Because you have a change in momentum over a change in time. Now, we're not going to do the derivation because the derivation would take 20 to 30 minutes. But change in momentum over change in time, that's a net force. And if I take that net force and I apply statistics, and in this case, the statistics is very simple. I have a bunch of molecules hitting the wall, and assuming that the hitting on the wall is uniform, I can calculate the average pressure, that is the average force per unit area, by taking the time it's going to take for a molecule to go across and back, and say each molecule has one collision per that time on average, multiply by the number of molecules, and I get an equation that gives me the pressure as a function of the speed of the molecules. Because the molecules are going faster, the time it takes to go back and forth is shorter. And the change in momentum is bigger. And then I have to, of course, take into account that the molecules are moving in more than one direction. And if I'm looking at this wall that's in the x direction, I don't care about the y or z components of the velocity. But the total kinetic energy has to do with the y and z components as well. And so we have a mathematical way of taking that into account. And doing all the work, we end up with a relationship that says, this is the relationship we end up with. 1/2 the mass times, anybody know what the greater than, less than sign means in this equation? That is a funny way of saying average. So it's 1/2 mass times the average of the squared speed. Not the speed averaged and then squared, but the average of the squared speed. And that's an important distinction. Is equal to 3 times pressure times volume over 2 times the number of molecules. That's the outcome of the derivation. But 1/2 mv squared is kinetic energy. And so if I have 1/2 m average of v squared, assuming that my masses are all the same, I can move that average out and make this the average of 1/2 mv squared, right? If m is constant and 2 is constant, which obviously 2 is constant, then 1/2 m average of v squared is the same as the average of 1/2 mv squared. But what is 1/2 mv squared? It's the translational kinetic energy. And so that's why I have on the left side of the box the average of the translational kinetic energy. Now on the right-hand side, I have 3 PV over N, but if we use the ideal gas law, this whole derivation was for an ideal gas, then PV equals nRT, so PV over N is KT. So this here is just using the ideal gas law. And there are 2 important outcomes then that come from this equation. Important outcome number 1, so I'm going to erase all of my markings now. Important outcome number 1 is that the average kinetic energy is proportional to the temperature. So what I said before, I said it without any backing. Now we have the backing for, and I'm going to be really specific now, for a monatomic ideal gas. That means an ideal gas that the molecules are single atoms. Give me an example of a monatomic ideal gas. Nitrogen's diatomic. Two nitrogen atoms bond together to form a diatomic molecule.
And a noble gas.
A noble gas. Helium, neon, argon, krypton, xenon, radon. Those are not very common. Those would be monatomic ideal gases. So it's not like we have a lot of them. So for a monatomic ideal gas, this is absolutely true. Kinetic energy average is 3/2 kT. That's one important outcome. The second important outcome, you have a question, Claudia?
Yes, just like on the, I know you, like we already talked about this, but like the RMS, so like that equation, you're taking the average squared. So the velocity squared and then the average of that velocity squared?
Good segue to the next important outcome. The next important outcome is about calculating the speed from this equation. So if I change colors here so we can see what I'm doing. If I take this term and this term, I have 1/2 m average of v squared equals 3/2 kT. And if I want to solve for speed, the first thing I do is multiply both sides by 2 and divide by n. And then I have the average of v squared is equal to 3 kT over m. What m is this, by the way? Is it the mass of a mole or the mass of a molecule? Molecule. The easy way to know is by seeing, is it K or R? If it was R, it would be mole. If it's K, it's molecule. And you'll see problems that use like capital M and lowercase m, and sometimes they mix them. So just be sure that you know what you're doing. If you use K, you better be using the mass of a molecule. If you use R, use the mass of a mole. So that's the average of the squared speed is 3 kT over m. And so the thing that we want to do is simply take the square root of that to get v, right? But there's a catch. And the catch is the square root of the average of the squares. Now let's just do a very quick calculation to see what's going on. And while I don't have space to do this, so I'm actually going to change to here. Go down. We're at least 3 slides in. Let's suppose that we have 3 molecules. 1, 2, and 3. And we have the speeds that are also conveniently 1, 2, and 3. Units of, I don't care, meters per second. And so speed squared, what's the square of 1? Duh. What's the square of 2? This is something you should just blurt out, please.
3.
Somebody besides Max. What's the square of 2?
4.
There we go. I'm asking questions to make sure people are following along. What's the square of 3? All right.
The way you said it threw me off. My brain couldn't.
Okay, well, we got it straight now. So now let's calculate the average. What's the average of 1, 2, and 3?
So, 3. That was 2. 2.5.
Okay, we're going to do this like we don't know anything. To find the average is 2. You add them up and divide by the number of items. That's 1 plus 2 plus 3 divided by 3 items. And so that's 6 divided by 3 is 2. Now, what's the average of the speeds squared?
14 divided by 2.
It's what? Okay, 4 2/3. So we want to see the difference between the average speed and the square root of the average of the squared speed, because RMS means, stands for root mean squared. And the way you calculate the root mean squared is first you square it, so that's what the third column is. Then you take the average, that's what we have in the yellowish color or orangish color, and then you square root it. So first we squared it, then we did the mean, now we're going to square root it. And what's the square root of 4.67? Equals 2.16. So the RMS speed for this simple collection of 3 molecules is 2.16, whereas the average speed is 2. They're different. The RMS speed is always going to be greater than or equal to the average speed. The RMS cannot be smaller. So the RMS speed is not the average speed, it's a different number. But it still has to do with the motion. It's because we're taking the average kinetic energy and trying to find the average speed from it.
RMS will always be bigger than average.
Yes. I did not do any woo clap for you today. Which kind of energy is proportional to the temperature in a monatomic ideal gas? Just to make sure we remember from the kinetic theory. Total kinetic energy, that's right. The total kinetic energy was proportional to temperature. And now when I said total kinetic energy, it was all translational. Oh, wait. Well, yeah, the total kinetic energy is proportional. Average is actually what we had. It's all translational kinetic energy if you have a monatomic ideal gas. If it's not monatomic, then it can be different. And I don't have a slide for this, so I'm just going to throw it out right here. If you have a diatomic ideal gas, here's a diatomic molecule. In chemistry, how did you model a diatomic molecule? You said the bond behaves like what thing? I know because they come and borrow these from me. In like general chemistry, you say that bond behaves like something physical. Yeah. It behaves like a spring. And so if I have a diatomic molecule, it's like a spring holding 2 masses together, and it can oscillate like this. So we call that vibrational energy. And it actually can store energy in kinetic energy of the vibration and potential energy of the spring. So we call each way that energy can be stored a degree of freedom. So if you have a diatomic molecule, it has 2 additional ways it can have energy besides translational kinetic energy in vibration. So we're going to count degrees of freedom for one molecule if it's diatomic. So kinetic energy translational is 3. Now, I have to tell you, what does degree of freedom mean? It's a way it can have energy. In translational, we have 3, and instantly you should question me. Because kinetic energy is a scalar, right? It's moving. It has kinetic energy because it's moving. The way we get 3 here is we have momentum is a vector momentum in the x direction, y direction, and z direction. And we say that the kinetic energy is 1/2 momentum in the x direction squared over mass plus 1/2 momentum in the y direction squared over mass plus 1/2 momentum in the z direction squared over mass. So that's why it's 3 degrees of freedom there. 3 ways it can have energy. 1 for momentum in the x direction, 1 for momentum in the y, and 1 for momentum in the z. So we have 3 degrees of freedom from translational kinetic energy. For vibration, I should have just put translation there because they're all vibration. We can have 2, 1 for the spring potential energy and 1 for the kinetic energy in vibration. And then there's one more way that it could have energy from your probably organic chemistry class, those have taken. Do you remember what the final way it can have energy is for a diatomic? It's rotation. Now rotational kinetic energy, remember, was 1/2 I omega squared. If it's diatomic, it can rotate about this axis, right? Or it can rotate about this axis, or it can rotate about this axis. But the moment of inertia was mass times radius squared. About this axis, that's going to be this mass times 1/2 of the separation squared plus 1/2 of the separation squared in this mass. Likewise, this way. But if it's this way, what's the radius? 0. So there is no kinetic energy for rotation about that axis. There's only 2 rotational kinetic energy options. So you have 2 degrees of freedom there. So far, this is not connected to anything. And so now I bring in a new term, the Equipartition Theorem. Okay, the Equipartition Theorem, if you break down the word, it actually makes perfect sense. Equa, what does equa mean? Equal. Partition, separated. Equipartition theorem means equally separated. The energy is equally separated between all of the degrees of freedom. With one additional piece of information, the equipartition theorem says it's equally separated with 1/2 kT in each, that's a each, degree of freedom. So if it was monatomic, how many degrees of freedom would a monatomic ideal gas have? Monatomic ideal gas, it's not held together by a spring, so you don't have any vibrational, right? It also is a point mass, so it has no moment of inertia. So how many degrees of freedom does a monatomic ideal gas have? Well, it still has the translational, so it has 3. And so for a monatomic ideal gas, you have the average energy was 3/2 kT. Notice I said the average. If you take the total number of molecules multiplied by n, so the total energy is n times 3/2 kT. If you have a diatomic, if you're at low temperature, there's some weird quantum physics that comes in, and the quantum physics at low temperature says you don't have enough energy to make it vibrate or rotate, which is really bizarre. Because in normal life, how much energy does it take to make something rotate? Well, I can make it rotate really, really slowly. So any energy would be enough to make something rotate. And when I say real life, I mean the life we're normally accustomed to. But in quantum mechanics, we can't make it rotate unless we reach a certain threshold of energy. And so at low temperatures, you can't make it rotate. And at low temperatures, you can't make it vibrate. quantum mechanics says that you can only have something vibrate or like a pendulum. It can only have certain amounts of energy. You can't have a really small amplitude by swinging the pendulum. It has to have a certain amplitude or certain amplitude, which seems bizarre. That's where quantum physics is bizarre. Looking forward to it, right, David?
Yeah.
Yeah. So if you have a cold diatomic ideal gas, it's still going to have 3 degrees of freedom and have the total energies 3/2 kT. If you warm it up, you get to the point where, I can't remember which one comes in first. Somebody that's taken organic recently might be able to correct me on this. Either vibration or rotation, one of them has the lower energy, and so that one comes in. And so it goes up to 5/2 kT. And if you go even hotter, the last one is accessible and it goes to 7/2 kT. Pretty bizarre, isn't it? And so in a later lecture in thermodynamics, I'll actually bring this back. But this is the time when it naturally comes into play. Okay, going back to our normal presentation. We've already answered that question. Maxwell-Boltzmann distribution. The Maxwell-Boltzmann distribution, Maxwell, that's James Clerk Maxwell, whose last name was Clerk, but his father inherited the estate from somebody whose last name was Maxwell, and so they added the name Maxwell. So James Clerk Maxwell, with Clerk being his family name and Maxwell being the adopted name from his father inherited the estate. Wow. He and Boltzmann calculated if you have a bunch of molecules and they're bouncing off of each other, how are the speeds of the molecules going to be distributed? It's a statistics problem. Remember, thermodynamics is called statistical physics. And what they came up with is that equation in the top right, that the probability of having some speed v is equal to this thing in parentheses, raised to 3/2 power, times 4 pi v squared times e to the minus 1/2 mv squared over kt. Now, if you notice this, 1/2 mv squared, kinetic energy, right? So that exponent is kinetic energy over kt. Kt is an energy term that's telling us about how much we have in each of the available partitions. And so if you plot that out, you get a curve that looks something like this. So that's what the distribution of speeds of molecules looks like as a function of temperature. If you raise the temperature, then they're going to be going faster and it moves out. So if you look at the right picture, the green line has a higher temperature, so you have higher speeds available. Now notice this curve is not symmetric. There's important things to pick out of this. First of all, the most probable speed. If I were to measure the speed of 500 molecules, the most probable speed would be the speed I'm most likely to find. I'll have let's say 10 of this speed and less than that of all the rest. The most probable speed is the peak. The RMS speed, well, what do we say about the RMS versus the average? Which is bigger, RMS or average? RMS. So the RMS is somewhere out here. Where would the average be if the RMS is out here?
Behind it.
It'd be somewhere between these two. And what we would have done in class yesterday, what we will do in class in 6 days, is we will do the calculations, calculus calculations, to find the most probable speed, which is going to be the speed where this equation has a slope of 0. And then we'll find the average speed, which turns out to be 1.13 times the most probable speed. And we'll find the RMS speed, which is 1.22 times the most probable speed. So if you know what the RMS speed is for an ideal gas, using the Maxwell-Boltzmann distribution, you can calculate what the average speed is as well. I know this is confusing. Does anyone have a question they feel comfortable articulating?
What exactly do you want us to know?
Okay, what do I want you to know? That's a very important question. Number one is I want you to know what the kinetic theory of gases is. That is the calculation that relates the motion of individual molecules to macroscopic variables, which are temperature, volume, number of molecules, and pressure. And that the outcome of that is that for monatomic ideal gas, the average kinetic energy is 3/2 kT. And then we also get the RMS speed is square root of 3 kT over m. So that's the first thing from the kinetic theory of gases. Second thing, that this Maxwell-Boltzmann distribution is not symmetric, and you have the RMS speed is faster than the average speed, is faster than the most probable. On the test, you will have these equations here. So you'll be able to relate them on the, you don't have to memorize like what their relationships are. But you need to have that understanding of what's going on and why. And then, of course, we'll probably do a calculation or two, like what is the RMS speed if I have room temperature hydrogen gas. Let's just, for grins, let's do that. Room temperature hydrogen gas. Still 3 degrees of freedom. Why is it important that I specify still 3 degrees of freedom? If it was monatomic, it would be 3 degrees always. If it's diatomic, I could have 3, 5, or 7, depending on the temperature. So 3 degrees of freedom means that I have kinetic energy average is equal to 3/2 kT. VRMS is equal to square root of 3 kT over m. K, Boltzmann's constant, 1.38 times 10 to the 23rd joules per Kelvin. Temperature. If it's room temperature, what is room temperature? It's what? It's actually, at least in physics, in different disciplines have different definitions of room temperature. Some people say 15 degrees Celsius. Physics says 20 degrees Celsius or 68 Fahrenheit. So 20 degrees Celsius, when I say room temperature, I mean 20 degrees Celsius. So what do I put in my calculation here? I have to put it in Kelvin because it's not a change in temperature. So it's 293 kelvins.
I'm trying real hard.
Yeah, I understand. Much like I wasn't here apparently on Monday. Okay, then what do I have on bottom? The mass of one molecule of hydrogen. Well, what's the mass of one molecule of hydrogen? One molecule is 2 atoms, and each atom is 1.008.
Yes.
Yeah, 1.
Yeah.
My eyesight isn't what it used to be, let's be honest. So I have, what are the units of this? That's not an A. What are those units? Atomic mass units. So then I need to convert from atomic mass units into what? Into kilograms. Oh, it should be multiplied by 2. Yes, so that 2 is because it's diatomic, 2 hydrogens. And then I need to have U on bottom, kilograms on top, not grams. What's the conversion? I don't have it memorized. Somebody want to look real quickly at the conversion between atomic mass units and kilograms?
-0.7. AMU per kilogram. 1.66.
I believe that should be kilograms per AMU.
Yeah.
Because 1 kilogram is, here's the way I do it if I have nothing else to do. 12 grams is equal to 1 atomic mass unit, or 12 atomic mass units times Avogadro's number. Because that's how you define the mole. And so obviously that should be 1 divided by Avogadro's number, except for then we have to convert from grams to kilograms. So now if we put these numbers in the calculator, and since we've come this far, let's finish out a problem. What do we get for the RMS speed of the hydrogen molecules at room temperature? I know it's hard to read my number there. I'll rewrite this while you're 1.6605 times 10 to the minus 27. A question or have an answer, sir?
I'm not sure that's right. But it's
It's going to be in the hundreds. I probably have this exponent wrong. What's this? Is k 10 to the minus 38? It is, right? Or 10 to the minus 22. That's a minus there. Because otherwise we would have a number that would be in the ballpark of 10 to the 20th. That would have been a mistake. It's 23. I'll join you.
What kind of number should we get?
Something in the hundreds.
Okay, I definitely did not.
Whoops.
Got something for the 25.
1,930.
You got 1,903?
Or 1,930.
Okay, I'm going to believe that's probably correct. Right? I didn't do the calculation myself. I'm trusting, and it could be an error, but it's moving relatively fast. If we had done nitrogen, how would the number differ? We're not going to do the calculation, but how would it differ? What would be different if we'd done nitrogen? Okay, the mass, instead of being 1.0079 times 10 to the 2, it would have been somewhere in the ballpark of 14 times 10 to the minus 2. And so it would be a smaller speed. And if you do the RMS speed for nitrogen, it comes out pretty similar to the speed of sound, because the speed of sound is the speed at which a wave is traveling through primarily nitrogen. All right, we're out of time. Did not get to where I wanted. I am actually going to postpone the next perusal assignment because I did not get to where I needed to be.
So not
Right,
but we have 2 homeworks.
but 2 homeworks, right.
It makes sense to lose.
That's too.
Yeah.